All right, so in this video, we're going to be talking about sequences and summation notation. It's very straightforward. The first three sections are going to be kind of easy. It's when you have to start guessing or trying to figure out what the relationship is that kind of makes this a little bit more difficult. So first, let's just go with the book definition of what a sequence is. A sequence is a function, A, whose domain is the set of natural numbers, and the terms of the sequence of the function values are A1, A2, A3, all the way up to AN. The AN just means, let's keep going till N, till N equals some value. All right, so each one of these is going to be a different number within the sequence that we have, okay? Normally, we just write the terms like this. A1, A2, A3, all the way up to A sub N. The three dots on the far right-hand side are called ellipses, and they just mean to keep going, all right? Now, you've seen and you've actually looked at a bunch of different sequences before. The most famous one, even your book goes over this, is going to be the simple sequence where A sub N equals 2 to the N, where N equals 1, okay? So what we do here is we say, well, A1 is going to equal 2 times 1, which is 2. A2, which is our second element within this sequence, is going to be 2 times 2, which is 4. A3 will be 2 times 3, which is 6. And we would just keep doing this for AN, which equals 2N. And if you've noticed, these numbers that I'm generating are all even numbers. All right, so this is nothing more than just a sequence of even numbers, okay? And what we're doing here is we're listing out every single term. So A1 is going to be our first term. A2 is going to be the second term. A3 is the third term, and so forth. So in the first couple homework problems I assigned, I'm just asking you to find, let's say, the first 5 terms of a sequence. And I may do something like this. I may give you the sequence -1 to the n power over, maybe you don't know what factorials are. So we'll just leave it as -1 to the n over n, okay? So what you would do here is just say n, maybe create like a little table. That would be nice. So we're going to say n equals 1, 2, 3, 4, and 5, because we want the first 5 terms. So 1, 2, 3, 4, and 5. And then what you would do from here is just substitute every single one of these values of n into the sequence that I've given you, which is -1 to the n over n. And what's really cool and interesting about this sequence that I gave you here is, and I'm going to write this in red so you know exactly what I'm talking about. When we have this -1 to the n power, or -1 to the n plus 1, or like -1 to the n minus 1, doesn't really matter. But all this does, this term right here, what it allows us to do is it gives us an opportunity to alternate between positive and negative signs. All right, now, initially, you're going to look at that and you're going to go, okay, yeah, that's pretty simple. But later on, especially in like Calc 2, when you were looking at different types of series, whether they're Maclaurin or Taylor series, and you're doing these tests for convergence, that -1 to the n power drastically changes how we view some sort of sequence or something like that. So let's just go ahead and let's figure out what each one of these terms are. So we're going to get -1 over 1, which is -1. So there's our first term. Then we get -1 to the second over 2. Well, that's going to be positive 1/2. Then I think you can see where this is going. This will be -1/3. Then we got positive 1/4, and then finally negative 1/5. Okay? So the first couple of homework questions, that's really all I'm asking you to do is just list out some terms. That's all. That's it. Very straightforward. Now, with the next example here, I'm going to be changing up the directions here a little bit. What I'm going to do here, if it'll let me change my pen, I'm going to give you a sequence. So given the sequence, find the nth term. All right, so we're going to start off with a really easy one first. All right, so we have the odd numbers, 1, 3, 5, 7, 9, okay? Now, if you want to go ahead and start finding some sort of a series or a sequence to generate these numbers, what I'm really asking for is, what does a sub n equal, okay? I want to be able to say, okay, well, given this a sub n, and I can let n equal 0 if I wanted to, I can let n equal 1 if I wanted to, I'm going to let it equal 1 for this one, okay? What I want to do is try to figure out what is the formula that will generate 1, 3, 5, 7, 9, and so forth, okay? So sometimes it's really easy, like this case right here, where all you really have to do is just think about it. And we're going to use our knowledge of the previous sequence that we looked at. So if I think about even numbers, all right, if I think about even numbers, I know that 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. And so forth, okay? Oops, sorry. Got these backwards. 2 and 4. There we go. Now, if you want to generate odd numbers, what you really need to do is just, you really need to know, like, okay, well, what's the even number? And then all I have to do is subtract 1. So for odd numbers, and this is the one we're looking at, let's try that guess that we have. So we're going to say a sub n equals 2 to the n minus 1 for n equals 1, 2, 3, and so forth. Now let's see if we're correct. Now, it's always good to test out 3, possibly 4 terms to make sure you were generating these terms respectively. Sometimes you may generate only the first 2 and it works, but then it doesn't work for any of the other ones. So make sure you try a couple of them. So a1 is going to be 2 times 1 minus 1. Well, that equals 1. Check. a2 is going to be 2 times 2 minus 1. Well, that's going to be 3. Check. a3 is going to be 2 times 3 minus 1. Well, that's definitely 5. Check. Even if we wanted to keep going, a4 is going to equal 2 times 4 minus 1, and that equals 7. So that's good. So we are generating these terms right here. So given the sequence, what is the nth term? Well, the nth term is 2 to the n minus 1. Okay? Now, sometimes it's easy like this. However, other times it's not that easy. So let's look at this. How about, let's see here. I want to do, how about negative 5, comma, positive 25, comma, negative 125, comma, positive 625, and so forth, okay? So when I take a step back and I look at this, first thing I notice right off the start, I have alternating signs. It starts off negative, then it goes positive, then it's negative, and then it's positive. So I know whenever I have those alternating signs, I'm already thinking negative 1 to the nth power, okay? Now, what I need to make sure is the very first term has to be negative. So if I start off with negative 1 to the n, I want n equal to 1, 2, 3, and so forth, because I know the very first one will be negative 1 to the first power, which is negative 1. Now, if we look at the 5, 25, 125, 625, hopefully by sitting there, you're looking at that and you're going, oh, those are just exponential powers of 5 respectively. So this would be 5 to the n. And like I said, check some numbers first, make sure it works. A sub 1 is going to be negative 1 to the first times 5 to the first, and that's going to be negative 5. Check. Your next term is going to be negative 1 to the second times 5 to the second, which is positive 25, so that's good. Your third term in the sequence is going to be negative 1 to the third times 5 to the third, so that's going to be definitely negative 125. So this is looking like it's working. The last example I'm going to do is actually another really famous one. And to a keen eye, you would see what it is, but, you know, maybe you don't see it. So we're going to do 1, 4, 9, 16, 25, and 36, and keep going. And if we want to find the nth term, well, these numbers, hopefully you could see them. Like I said, it's pretty. I think it's pretty straightforward. These are nothing more than just what we call square numbers. Okay, these are just square numbers. And the reason why we call them square numbers, well, some of you may be thinking, well, it's 1 to the second, 2 to the second, 3 to the second, 4 to the second, and so forth. And I completely agree with you on that one. In fact, our sequence here is just going to be a to the n equals n to the second power for n equal to 1, 2, 3, and so forth. But if you've ever wondered, well, where does this square come in? Well, if we were just to draw the pictures of each one of these numbers, we are drawing perfect squares with just little dots that represent each one of the values respectively. So that's why when we say like 1 to the second power, if we say 1 squared, it's because literally you were creating squares with those numbers. Okay? Now, there are other famous types of sequences that exist, all right? And quite possibly the one that everybody knows is the one I'm about to go over right now. But before I do that, I want to define what type of sequence it is. So we have what we call recursively defined sequences. And the very simple definition of this is just you were starting off with some sort of information, and then you were using that information to find the next term. And then every term after that, you're going to use the information that you previously have gained to find the next term. So a really simple one is something that looks like this. So we have a sequence a sub n equals 3 times the quantity a to sub n minus 1 plus 2, where a1 equals 1. So this is called a recursively defined sequence. And what makes this recursively defined is the fact that we have this starting value right here. And we're going to use this starting value to find every single term within our sequence. So we know the first term, a1, is going to be 1. Then a2 is going to be 3 times the quantity a sub 2 minus 1 plus 2, which simplifies to a times the quantity a1 plus 2. And we know a1 is 1 from the previous step. So this will be 3 times 1 plus 2, which equals 6. Okay? Actually, what am I talking about? Equals 9. Sorry about that. The best of us make mistakes all the time. So a3 is going to be 3 times a sub 3 minus 1 plus 2, which simplifies to 3 times a sub 2 plus 2. And we know a2 is from the previous step. It's going to be 9, so this would be 3 times the quantity 9 plus 2, which is 33. Okay? So if we kept doing this, we would find that the first terms are 1, 9, 33, 105, 321, and you would just keep doing that, and that would generate this sequence. Now, quite possibly the most famous one that we've ever seen is this sequence right here. Okay? This is called the Fibonacci sequence. And there are so many different applications to the Fibonacci sequence. Okay? Now, the Fibonacci sequence, its general form looks like this. The first term is 1. The second term is 1. And then the nth term is going to be the Fibonacci number, so fn-1 plus fn-2. Okay? So, if we know f1 equals 1 and f2 equals 1, f3 is going to be f3 minus 1 plus f3 minus 2. And if we simplify that, that's going to be f2 plus f1. Therefore, 1 plus 1 equals 2. So our third Fibonacci number is 2. And if I just zoom out here, I can go ahead and start labeling this stuff for you. So let me get out a different color. So here's F1. There's F2. There's F3. There's F4. There's F5 and so forth. Okay? So one of the coolest applications to this Fibonacci sequence is actually in the Fibonacci Spiral, which you've all seen before. And, you know, there's always pictures. Usually it's in a math book. You see this picture and everything. But now we can go ahead and we can start exploring this. Because if we start all the way inside this square, and I'm going to try to highlight it here in red. Actually, you know what? No. I'm going to use blue. Notice here, this first square, hopefully you can see that. That is a square where we have, it's one side by one side. Then we have another square to the left of it, and that is another 1 by 1 square. Now, if we just keep bringing this out and we create a square right here, let me use a different color, because I did the two ones in blue. Now, if we were to draw a square on top of that, that's 2 by 2, which is right here. Okay? And we just kept doing that. So 1, 1, 2, and then 1 plus 2 is 3. So here is our third square. I'll do this one in black. So here's our square. That's 3 by 3. And then 2 plus 3 is 5. So that's this square right here. And then 3 plus 5 is 8. So that's this square right here. And then 8 plus 5 is 13. And we just kept building this square, okay, using the Fibonacci numbers. Something unbelievable ends up happening, okay? And maybe you've heard this before, maybe you haven't, but I'm going to go ahead and I'm going to show you this real quick, all right? So if we were to take, excuse me, any one of these rectangles that we're creating, now remember, we're creating squares using Fibonacci sequence. However, if we were to look at the ratio of a rectangle, so for example, we're going to do this one right here, okay? So we're going to do this rectangle right here. Okay? Oops, sorry. And we were to take the ratio of this rectangle. So that rectangle there is going to be 21 over 13. It's the previous two Fibonacci numbers, okay? And we were to divide these two numbers. What you're going to get is 1.61538 and a bunch of decimals after that, okay? Now, if we go ahead and take the next two Fibonacci numbers, so we're going to do 21, which is here, and then 34, which is here. So 34 over 21, and we were to take that ratio there. You get 1.6190 4719 and all this other stuff, okay? What's happening here is this. If you take the ratio of all the Fibonacci sequence numbers, it will converge into a very special number that we call the golden ratio, which is 1.618 and some other decimals after that. So if you're really interested in like where number or how we use Fibonacci sequence, or better yet, just numbers in general, I would definitely Google the golden ratio and just take 5 minutes and read about it. It is unbelievable. This ratio, this golden ratio that we're talking about, exists in all living creatures. So you're about to see my artistic ability here. So here's a human. That's us. If you were to measure the height of yourself from the floor to the top of your head, and then where your belly button is, and measure that from the belly button down to the floor, okay? And you were to take the ratio of your height and then your belly button, that equals 1.618. And it'll be a little off because our measurements aren't exactly precise. However, you're going to get really close to this, okay? Same thing if you were to look at someone's face. All right, so here's their eyes, there's their nose, smiley face right there. If you were to take the distance from the top of the head to the chin, and then from the nose to the chin, and divide those two numbers, you get 1.618. You could do the same thing with your shoulder to your finger, middle finger, and then your elbow to your middle finger. You get 1.618. You could do this with your cat. You can do it with a dog. You can do it with a bee. You could do it with flowers. In fact, when you look at sunflowers, all right, let me see if I can grab a picture real quick. All right, I'm back. I literally just Googled this, all right? I clicked on the first website. Amazing examples of Fibonacci sequence in nature. You got a chicken egg. You got Romanesque broccoli, aloe plant, the spiral chili pepper, the sunflower, all right? If you were to just start in the middle of the sunflower, you would have one little petal, one little ridge, and then you'd have another one next to it. And then next to that, you'd have 2. And then you would have 5, and then 8, and then 13, and then 21, and it would just spiral out. A rock daisy, I don't even know what that is. I guess it's just a regular daisy flower. A pine cone, another one. Chameleon tail. All right. Ooh, that's disgusting looking. American giant millipede. Gross. All right. But yeah, here, they're all there. This Fibonacci sequence. And what's really cool, if I scroll all the way up, even hurricanes. The eye of the hurricane and the way that it moves around the earth is the Fibonacci sequence if you were to build it just like the Fibonacci spiral. Absolutely fascinating, all right? And it's really cool because now you're getting to that point in math where you're done understanding how numbers work. You got a really good understanding on how functions work. You know how to manipulate functions to solve for unknown variables. This sequence stuff is where it really starts to take off in terms of, how do we view our world using mathematics? So the next thing I want to talk about here, pretty straightforward. Nothing more than just partial sums of a sequence. And it's exactly what it sounds like. You are just taking a sequence and you're adding up a certain amount of terms, okay? So if we have just like a regular sequence that's called A1, A2, A3, and so forth, all the way up to A sub n, the partial sums are going to be A1 equals, obviously, A1. Sorry, let me write it like sums here. S1, the first sum, equals A1. S2 is going to be A1 plus A2. S3 is going to be A1 plus A2 plus A3. And you get all the way down to the nth partial sum, which is going to be equal to A1 plus A2 plus A3. And you just keep doing that until you get to AN. Okay? So this is nothing more than just adding up some numbers. And what's really cool about this is you can actually generate the famous numbers that we have. Okay? So let me do first an easy example. All right? And then we're going to do one that's a little bit more complicated. Okay? So let's find the first 4 partial sums given by A sub n equals 1 over 2 to the n. All right? So a1 is going to equal 1/2. a2 is going to be 1/4. a3 is going to be 1 over, what is that, 2 to the third, which is going to be 8. a4 is going to be 1 over 2 to the fourth, which is 16. So here are the first four numbers in my sequence. Our first partial sum is just 1/2. Our second partial sum is going to be 1/2 plus 1/4, which equals 3/4. Our third partial sum is going to be 1/2 plus 1/4 plus 1/8, which equals 7/8. And then our fourth partial sum is going to be 1/2 plus 1/4 plus 1/8 plus 1/16, which is going to be 15 over 16. Now, if we wanted to extend this problem a little further, okay, so let's just say this was part A. Part B is going to be find the nth partial sum. Find the nth partial sum, okay? Well, what we have to do here is we have to take our outputs for each one of the partial sums and create a sequence off that. So here's our sequence of the partial sums. It's 1/2, 3/4, 7/8, 15 over 16. Okay? Now, notice that in the value of each partial sum, our denominator, 2, 4, 8, and 16, they're all nothing more than just powers of 2 to the n. Okay? It's that numerator that we really got to be worried about. So the numerator is always one less than the denominator within each one of these partial sums. So like, for example, in the first one, the denominator is 2. However, the numerator is a 1. It's 1 less. And the next one, the denominator is a 4. The numerator is 1 less. And the third one, the denominator is an 8. Our numerator is 1 less. All right? So if our denominator is 2 to the n, then our numerator is going to be 2 to the n minus 1. It's always 1 less. And then if you wanted to, you can even simplify this further because you have a monomial in the denominator. So this will simplify down into 1 minus 1 over 2 to the n. And what this will give you, all right, this will give the value of any nth partial sum. So if you wanted to know, okay, well, if I wanted to keep doing this, all right, what is the 50th partial sum? 1 minus 1 over 2 to the 50th power, which is essentially, let me kind of do this here, which is essentially 1. All right, I'll leave that up to you to kind of do that on your calculator. But I mean, if you wanted to, like I said, you can easily just do the partial sum of S4. That would be 1 minus 1 over 2 to the 4th, which is 1 minus 1 over 1 over 16. We know if we wanted to just combine these two numbers together, it would be 16 over 16 minus 1 over 16, which is obviously 15 over 16. So as the partial sums get larger and larger and larger, for us, it looks like our value of the partial sum itself is approaching the number 1. So it looks like we call that converges. And you're going to be seeing that a lot, especially in Calc 2. Okay? So the next partial sum that I want us to look at is a very special one. And this is called a telescoping sequence. All right, so if you think of how a telescope works, and I mean like a really old one, not like one that you'd go on like Amazon and buy one of those Celeste stars or one of those Orion, Dobsonian or reflective telescopes that you can like look at the moon and Mars and stuff like that. I'm talking about the one that a pirate would use, where he sticks it up to his eyeball and he like pulls it out, okay, and it like this like little thing that looks like a can turns out to be a big telescope. That's what we mean by a telescoping series. So the most famous is just a very simple one. It's a sub n equals 1 over n plus, 1 over n minus 1 over n plus 1. All right? And the reason why this is so famous is when I start writing out the partial sums for this. So, like the first partial sum is going to be 1 minus 1 half. Okay? And then the second is going to be 1 minus 1 half plus 1 half minus 1/3, okay? And then the third one is going to be 1 minus 1 half plus 1 half minus 1/3 plus 1/3 minus 1/4, all right? And I'm going to do one more, okay? I'm going to write all these out. So our fourth partial sum is going to be 1 minus 1 half plus 1 half minus 1/3 plus 1/3 minus 1/4 plus 1/4 minus 1/5, okay? What's happening here, let me get out a red marker here. What's happening here is as we increase the number of terms that we want, okay? And I'll start with S2, so our second partial sum. Notice that you have negative 1 half here and then positive 1 half here. In other words, these are going to cancel each other out. Okay, so this collapses down into nothing more than just 1 minus 1/3. Now, if I look at the first partial sum, I can write 1 minus 1 half. So hopefully this makes a little bit more sense now. The third partial sum, notice that the 1 halves are going to cancel. The 1/3s will cancel. So this collapses itself down into 1 minus 1/4. The fourth partial sum, the 1 halves cancel, the 1/3s cancel, the 1/4s cancel. The only thing left over is going to be 1 minus 1/5. So this is what we mean by a telescoping sequence, is the fact that, if you were to expand this or contract it, you only get the first term and the last terms, and that's it. You get the first eyepiece and the last eyepiece. Everything in the middle basically collapses in on itself. So if we wanted to find the nth partial sum for this, all you have to do is just look at the outputs that you have for each partial sum. So obviously all of them have a 1 in common. They all have a minus. The numerator is a 1. And then if you look, you have 2, 3, 4, 5, and so forth. So we're going to say n plus 1 for n equal to 1, okay? And the reason why we got to start this at n equals 1, if you're asking, is because we started off with the first partial sum. So you got to make sure all that stuff lines up, okay? Now, the last thing we're going to go over in this first section is what we call sigma notation. So this is the first time where you're actually seeing something like this before. So let's say, I want a thicker marker. Let's assume we have the sequence A1, A2, A3, A4, and so forth, okay? And what we wanted to do is start adding up these numbers, adding up these partial sums, okay? Well, what we can do is we can rewrite this using what we call sigma notation. So let me show you how this looks, okay? First, you're going to use this fancy letter E, all right? That is the Greek word sigma. Let me write it down here. Sigma. And this stands for sum. Like, just keep adding things up. Now, depending on the book or depending on, what computer program you're using or something like that, the lower and upper bounds or the lower and upper limits will vary slightly. So our lower limit is right here, k equals 1. This tells me where to start. On the very top of the letter E is going to be the letter N or something of that nature, and this tells me where to stop. Okay? And then we will have A sub k, which is going to equal A1 plus A2 plus A3, and you keep adding this up all the way until you get to A sub n. All right? And this is what we call summation notation. The k is called the index, and the letter n is just tells us where to stop. Okay? So if we wanted to, we could just do like one or two like very simple examples here. Okay? So the first one is nothing more than just find a summation with k equal to 1. We're going to go to 3 of k to the third power. So this is going to be 1 to the third plus 2 to the third plus 3 to the third. And then if you were to add all these up, you would get 1 plus 8 plus 27, which is 36. So that's really all that this is. It's just a nice, quick, efficient way to write partial sums, but not partial sums really, but like just summations in general. All right. And you see this summation notation and everything. You're going to see it a lot with the further in the math world you actually go to. Okay. Now we do have properties using summation notation. This is just taken directly from your book. And what's really nice about this is we consider the summation symbol to be a linear operator, meaning we can use this on basic algebraic techniques. So we can distribute the summation symbol, and if we have a constant for step 3, because step 1 and 2 are just the same thing, or not steps, I'm sorry, property 1, property 2. Property 3 just says, listen, if you have a constant in front of a sequence, then you can take the constant and put it out front, because all you're going to be doing is multiplying every single one of those elements by that number anyways. So that's going to be it for this video. This is the start, I think, of a brand new world of mathematics that many of us have never really seen before. Okay? Hopefully, we can get to the point where I can start throwing in factorials. So, for example, we've all seen the number e before, and e is approximately 2.718 with a bunch of numbers after that. But e can be rewritten as the summation from k equals 0 to infinity of 1 over k factorial. And what this will do is it'll start to generate not only the number e, but all the decimal places, and it all depends on how many partial sums you want or how many terms do you want. So you can use this to your advantage to actually start generating numbers. In fact, to be honest with you, this is exactly how your calculator works. Whenever you type in e and hit enter, it doesn't have e stored. It has this summation, and what it does is it just adds up however many terms it needs to display it on your screen. I think the TI-83 is only good to about 10 or 11 decimal places. That's it. So anything after that, your calculator just says, well, we're going to round it to the 11th decimal place and call it a day. So I'm going to call it a day here. Enjoy, and I'll see you in the next video.